In this next section, which is 3.5, this is our the trig functions, we are gonna do a couple of little refreshers. We'll do quick proofs to figure out how we get these derivatives, and then we will work through some application problems. First, I'm gonna show you just a couple of formulas that you've already learned that will be helpful to us. So you might remember these two. These are our sum identities for sine and cosine. They look like that. And then the other two were the two formulas that we worked through when we covered our squeeze theorem. They're going to be useful to us as we navigate our way through finding derivatives for our trig functions. So we're going to start by taking the derivative of sine of x, and we're going to use our limit definition. So if we used our sum identity for sine, we would get this. Now, because we can, we're going to separate these fractions into two fractions. We're combining these two terms and putting it over h, and this term will be by itself. So we've got this. Now, you'll notice for this one, I can factor out a sine of x from the first fraction. So it looks like this. Now, don't forget these two limit functions that we know. And looking at the second one, if we can write that, we could factor out a -1, and we would get this. So let's look at what we have in our blue limit formula. We have this, and we have this. So we can replace those with what they equal. Now we can see the first of our trig derivatives. The derivative for sine of x is cosine of x. So to not take too much of your time, we do that same process with cosine. And you'll notice here, we used our sum identity for cosine. You'll also notice here, in this second step, we just took the two terms that had the cos of x's and we combined them into one fraction, and we kept the sine x, sine h separate. Next, you saw that we factored out a cosine of x. So we're going to identify this here. We're going to identify this because down below, that highlighted term becomes 0. This one becomes 1. And here is our cosine derivative. The derivative of cosine is negative sine. How do you think we're going to come up with the derivative for tan? Well, we're going to rewrite it as the derivative of sine over cosine. How are we going to come up with that derivative? Yes, we're going to use the quotient rule. And so you notice, if we do use the quotient rule, we end up with this expression, which we can then clean up to this, which then simplifies to this statement. So this tells us that the derivative of tan is secant squared. And I'll show you with this example for the derivative of secant, because we're going to just look at how all of the other trig functions derive. We're going to treat secant as 1 over cosine, which we then treat as cosine of x, all raised to the -1. And we're going to do the chain rule here. And I'm just going to write it out so that you can see this step by step. So you'll notice here, with this step, we used the chain rule. So our g of x is cosine. And here, we replaced the derivative of cosine with what it is. It's negative sine. And here, because we had that double negative, we rewrote it, and I brought that cos x to the bottom. Next, I separated it so that we had two cosine of x's instead of cos x squared. So that would be the equivalent of 1 over cos of x, so I'm here, times sine x over cos x. And then we replace those with their respective trig functions, secant x, tan x. So our derivative for secant x is secant x tan x. Here are the remaining trig derivatives. You'll see that it looks very similar to the previous ones of secant and tangent. So let's put these all in a nice package so that we can start working with them. Here they are. Write them down. Let's look at these two problems. I like putting them side by side because we can identify for both of these that these are both composite functions, but the f and the g are in different places. So you'll notice for the first problem that the nested function is the sine x, whereas in the second problem, the nested function is x to the 1/2. So let's do problem 1 first. That would be, that would make my f function here a power function. It's this to the 1/2. So that derivative would be 1/2, whatever's in there, raised to the negative 1/2. What's in there? The sine of x. What do we multiply by with the chain rule? The derivative of the inside. So we are multiplying by the derivative of sine of x, which leaves us with 1/2 sine x to the negative 1/2 times cosine of x. For problem 2, the outside function is sine of x. So when we use our chain rule here, we take the derivative of the outside function, which would be cosine, but we keep what's inside, keep that g, times the derivative of g. So that cleans up to this. Why don't you pause here and see if we can't, or if you can't work this one out. So if I were to first start with this problem, I would rewrite it like so. So it's clear what that outside function is and what the nested function is. And you might realize this is a nested function within a nested function. Let's keep going. So the first thing we're going to do is we're going to take the derivative of the outermost function. That's our f, and that's quantity cubed. So that would look like this. So you'll notice that this part is our f prime of g of x, and this part is g prime. And so now we still need to work out g prime. And you might see this is also a chain rule. The nested function in that is 7x squared. So our next step is to take the derivative of secant of 7x squared. The derivative of secant x is secant x tan x. So our answer is going to look like this. So now this is our f prime of g of x. The g is 7x squared. And this is our g prime. So this yellow portion has one last step. So it looks like this. And the last thing we do is we bring down the first part of our expression. And so it looks like so. And lastly, we might want to combine, just because we can, these two terms and make it look a little more clean. And there we have it. So for this example, we're asked to derive this expression. So our first step is we would rewrite it so that it's in this format and a little easier to follow. So you'll notice this is a blend of both the product rule and our chain rule. So let's separate them so that it's clearer to us that we're going to have to use our product rule, gf prime plus fg prime. So let's, for simplicity's sake, off on the side, evaluate both the derivatives of f and g. So this is f, and f is a problem in and of itself. So here we're going to use the chain rule to take f prime. So let's just evaluate that. So f prime, if we plugged our chain rule in, would look like this. So f prime, when we use our chain rule, would look like this, unsimplified. And then when we cleaned it up, it would look like this. And to tidy things up, we have this for f prime. Now let's evaluate g. So g is this expression. So when we take that derivative, it's another chain rule, which would look like this. And so when we want to simplify this expression, it would take us to this step, which we can then clean up to give this. What a doozy of a problem. What was I thinking? So now we're going to go back to that green and we just write them out. So you'll notice this is G. That's F prime. This is F. This is G prime. And I think the only thing that I might move, and I'm not going to rewrite it because this was a lot, is I might move that -10 here and say -10, but this, folks, is precious.